Hey guys, Mr. Backward here. In this video, we're going to look at some other consequences of the mean value theorem. Now, the first consequence that we're going to talk about is that functions with a derivative of 0 are constant functions. So if we know that the derivative of f of x equals 0 at each point of an interval I, then there is a constant c for which f of x equals c for all x values in that interval I. So going way back to when we first learned about derivatives, we said that the derivative of a constant function was always going to be 0. So for example, if your function was f of x equals 5, then when we did its derivative, any constant function automatically derived into 0. Well, because of the mean value theorem, we can actually take this derivative rule and really kind of work it in reverse. So if we know that a function has a derivative of 0, then, based on what we know about derivative rules, we know that the original function would have to be some constant value c. Now there's another consequence of the mean value theorem as well, and that's that functions with the same derivative differ by a constant. So if you've got the derivative of f of x being equal to the derivative of g of x at each point of an interval I, then there's a constant c such that your function f of x is equal to g of x plus c for all x values in I. So if we have a function, say f of x equals x squared, and our g of x equals x squared plus 7. Then if we find the derivative of our f of x function, well, the derivative of x squared from the power rule is just 2x. And if we look at this g of x function and find its derivative, well, use the power rule with x squared, and that's 2x. And if you differentiate a constant, then that just turns into 0. So even though these functions were different by some c value, they still had the exact same derivative. So what this is saying is kind of the reverse direction. If we know that these two derivatives are equal to each other, the derivative of f is equal to the derivative of g, then we know that they only differ by whatever this constant c value is. So in this example, we're going to do a derivative, but in reverse. And we want to find a function f of x whose derivative is negative sine of x, but the graph is going to pass through the point 0, 2. Now, using what we just talked about, if two functions have the exact same derivative, then they differ by some constant value c. So instead of thinking about what f of x is, I'm going to think about this function g of x. And I want to think about what functions do we know of that when we do the derivative, it would turn into negative sine of x. Well, one of our derivatives that we've talked about is for a cosine function. And we've said that the cosine derives into negative sine of x. So if g of x is the cosine of x, then we know that the derivative of g of x is equal to negative sine of x. But we're not trying to find this g of x function. We're trying to find some f of x function whose derivative is going to be this negative sine of x, but go through the point 0, 2. Well, because our two functions have the exact same derivative, that negative sine of x, then our f of x function must be some sort of cosine function, but it's got some c value constant being added onto the end. And what we want to try to do is figure out what that c value would be using the point 0, 2. Well, that point gives us an x value and a y value. So what we can do is use this f of x function, plug in x and y, and solve to find c. So our function value is the y value. So we've got 2 equals the cosine of 0 plus some c value. Well, from the unit circle, the cosine of 0 is 1. So we've got the equation 2 equals 1 plus c. If we're solving for c, I would subtract that 1 over to the left-hand side, so we get a c value of 1. So our f of x function must be the cosine of x plus 1. Now, that whole idea of doing a derivative in reverse is called an antiderivative. So a function capital F of x is an antiderivative of a function f of x if the derivative of that capital F of x is equal to little f of x for all x values in the domain of little f. And the process of finding an antiderivative is called antidifferentiation. Now, in this example, we're going to find a velocity and a position function given an acceleration. So we're going to find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following conditions. So the first condition that we're going to talk about is that the acceleration is 9.8 meters per second squared, and the body is falling from rest. So knowing that the body is falling from rest, well, we typically measure distance fallen in meters and the time in seconds. So we're assuming that the body is just being released at a time of 0. It's not being pushed or thrown. It's just freely falling without any outside influence. Now, knowing that the acceleration is 9.8 meters per second squared, we've talked about acceleration as far as being a second derivative. So we're trying to find an antiderivative or a couple of antiderivatives. So we know that our velocity, I'm going to call it v of t, we know that our v of t function is an antiderivative of the constant function 9.8. So we're trying to think about something that would derive into 9.8. Now, if we were to think about a function, let's call it g of t, and that function was 9.8t, then as we found its derivative, using what we know about the power rule and all that, this would differentiate into 9.8. So our velocity function, since they have the exact same derivative of 9.8, then our velocity function must be 9.8t plus some constant value c. And then, like we talked about earlier, this body is falling freely from rest. So what that means is that at a time of 0, then our velocity is 0. There wasn't any outside push or throw to this. It's just that split second that we let go, it's got a velocity of 0. So we can plug this information in here to help us figure out what that c value is. So when our t value is 0, so 9.8 times 0 plus c, we know that our velocity is also equal to 0. Well, 9.8 times 0 is 0, so then we just get 0 as our c value. So then our velocity function, v of t, must just be 9.8t. So that's the first part, finding the velocity function. But now we also want to find our position function. And the position function is the antiderivative of the velocity function. So we want to try to think about what function would give us this 9.8t if we did its derivative. Well, I'm going to introduce a new function, and let's call it h of t. And if h of t was, say, 4.9t squared, then as we would do the derivative of h of t, we would drop that 2 down as a multiplier, and 2 times 4.9 would be 9.8t. So our position function, which we've called s of t, must be 4.9t squared, but with some c value attached, since that would have the same derivative as this h of t function. Now again, to figure out that constant value, we are going to use a time of 0. And because we know that our object or our body was starting on the ground, then we know at a time of 0, then our position is 0. So we can plug that stuff in to help us find our c value this time. So if we know that 0 is equal to 4.9 times 0 squared plus c, well, 0 squared is 0, times 4.9 is still 0, so we know that our c value must be 0. So then our position function, s of t, is just going to be 4.9t squared. Now this example is going to be very similar, but with one slight change. So we're still going to find a velocity and a position function of a body falling freely from a height of 0 meters. We're still going to have an acceleration of 9.8 meters per second squared, but this time our body is going to be propelled downward with an initial velocity of 1 meter per second. So we still want to start by finding our velocity function v of t, and it's going to be very similar to what we did before. We know that we're looking for some function that when we do its derivative, we're going to get 9.8. And because of the stuff that we just got done talking about, we would know that this velocity function would have to be 9.8t. Because when we do the derivative of this velocity function, that t would go away and we would just get 9.8. But there's going to be some c value being added on the end. And here's where that initial velocity of 1 meter per second is going to come into play. We know that at the time of 0, at the split second that this object starts falling, we're propelling it with a velocity of 1 meter per second. The initial velocity is that 1 meter per second. So at a time of 0, our velocity is 1. Well, we're going to plug that stuff in. We know that our velocity is 1, and that's going to be 9.8 times our time of 0 seconds plus this c value. Well, 0 times 9.8 is 0, so we get 1 as our c value. So then our velocity function v of t must be 9.8t plus 1. And then as we're finding our position function, the position function is the antiderivative of the velocity function. So what we were talking about before, s of t, well, before we just had the 9.8t. That's still going to anti-differentiate into 4.9t squared. But now we've got this 1 attached to the back end. So if we anti-differentiate that, something that would give us a derivative of just 1 would be having an extra t on the end of this function, because the derivative of t would just be 1. But there's still going to be another constant attached on the end here. And what we know this time is that at a time of 0 seconds, we started on the ground. We started at a height of 0, so our position is going to be 0. So we're going to plug these values in to solve for our c this time. So our position was 0 at a time of 0, so both of these t values need to be filled in with zeros. Well, 0 squared is 0, times 4.9 is still 0. Add 0 to that, it's still 0. So we get 0 as our c value. So then our position function s of t is going to be 4.9t squared plus t. That's going to be it for this video. Thanks for watching.